How do we know the Earth has layers? The answer is earthquakes. Earthquakes create seismic waves that can be detected by scientists. The shifting rock in an earthquake causes vibrations. These are seismic waves. The waves that travel through the Earth can be detected by the hundreds of seismic stations around the planet. The seismographs can give data not only about earthquakes, but about the inside of the Earth itself. There are two main classes of seismic waves: body waves and surface waves. Body waves travel within the body of Earth. These include P waves, or primary waves, and S waves, or secondary waves. P waves cause the ground to compress and expand, moving back and forth in the direction of travel. They are called primary waves because they are the first type of wave to arrive at seismic recording stations. P waves can travel through solids, liquids, and gases. S waves move the ground in a shearing or crosswise motion that is perpendicular to the direction of travel. These are the shake waves that move the ground up and down or from side to side. S waves are called secondary waves because they always arrive after P waves at seismic recording stations. Unlike P waves, S waves can only travel through solid materials. There are 268 seismic recording stations around the globe, so whenever there is an earthquake we can get data about the direction and speed of the seismic waves. Can you see in the data where the waves hit at each station? If the Earth were made of the same materials all the way through, we would expect the waves to move like in this graph. The waves go through the Earth at a near constant and even speed. But that's not what the waves do. They move as predicted at first, but then the patterns become uneven. If we measure the geocentric angle from the epicenter to the anomaly in the data, we find that the wave seems to deflect at an unexpected angle. On this model of the Earth, we mark the epicenter of an earthquake. Using our data from seismograph stations around the world, we can draw out the angle of direct P waves from the earthquake. Now that we know the angle, we can draw the direct path of the P wave from the epicenter of the earthquake to the seismograph station. But this doesn't just happen on one side of the earthquake. P waves spread out in all directions. We will represent this on our model by drawing the path of the P wave on the other side of the Earth. We see this same pattern from many earthquakes around the entire world. We will cut out the angle on our model and use it to trace the angle of direct P waves from many different earthquake epicenters. Observe what patterns emerge on the planet model when we show the data from many different earthquakes. Have you been able to detect the pattern? A shadow in the center of the model shows that there is an area in the middle of the Earth where we do not detect any direct P waves. This leads scientists to believe that the center of the Earth must be made out of something different than what is around it. The data shows that some waves do go through the center of the Earth, but they change direction or speed in this area. When we combine all the seismic wave data, we can get a picture of layers inside the Earth.